Hey folks, we're going to talk a little more simple harmonic motion and specifically about something called physical pendulums. And I've written down two things. A quick review of anything in simple harmonic motion has a linear restoring force, and that leads to the following. You can write the acceleration in terms of x, and whatever's in front of the x is omega squared. Do remember this is a second order differential equation. So like what I mean by that is the acceleration is the second derivative of position. The first derivative is velocity, and then you got acceleration. So you can rewrite this as or the second derivative, and how you write that is like that, which is kind of weird, I know, but that means second derivative, and you get negative omega squared x. So that means the second derivative of x equals negative omega squared x. That is a property of simple harmonic motion. And then once you got that omega, that angular frequency, you can then find the period by saying 2 pi over omega. Now, we're going to do one more thing with this. Let's say we have a simple pendulum, and you would have done this last year. You would have had a string and a little pendulum bob. I don't know why they call them bob, but they do. And last year, your teachers would have said, well, the period of that is 2 pi root, well, do you guys remember? Well, it turns out it's L over G. Now, where does that come from? Okay. Well, a pendulum isn't moving linearly, it's rotating. So instead of saying A equals negative omega squared x, we're going to divide both those by r. Okay. A divided by r is alpha, and x divided by r is theta. So in rotation, we can rewrite this as alpha equals negative omega squared times theta. Now, a quick note on this. This omega is not the angular speed of the pendulum bob. That omega is the angular frequency of the pendulum bob. They are related, but they're not the same thing. Okay, so just an FYI. All right, so let's actually get alpha in terms of theta. So the theta we're talking about here is from the vertical. So there's your theta. To get alpha in terms of theta, well, you're going to draw an FBD. And I'll save you the trouble. I'm just going to draw the component version of this. So you're going to have a component of mg pointing parallel to the motion. That'll be sine of theta. You're going to have a component of mg pointing perpendicular to the motion. That is cosine of theta. And then you're going to have the tension, force of tension acting up. Okay. Now, by the way, the force, if this thing is swinging right now, if it's moving, the tension will be bigger than mg cosine theta. And we've done in previous units, we've talked about how to calculate that tension. But in this case, that's not what I'm worried about. What I want to know is how fast is this thing angularly accelerating, and that's being caused by mg sine theta. So if I do, and you're going to have to do this in all these, net torque equals I alpha, okay, and net torque about some axis. Well, the axis we're talking about for a pendulum is it's pivoted at the edge of the string there, so that's going to be our axis. All right, so the force of gravity that's perpendicular to the motion, well, that torque would be R times mg sine theta. Now, one last thing, we're going to throw a negative in front of that. And you might be like, well, why? Okay, well, it's real simple. If the pendulum is displaced left, the torque is the other way, right? Okay, or if I displace the pendulum counterclockwise or clockwise, the torque will be counterclockwise. So the torque is always in the opposite direction of the angle or the angular displacement. So that's why the negative is sitting there. Now, it's a pendulum bob. What's the moment of inertia? Well, it's simply mr squared and then alpha. Okay. So we can do a little tidying up here. One of the r's drops out, right? And the m drops out. So as you learned last year, the mass of the pendulum bob doesn't matter. And I'm pretty close here. What I'm going to eventually get is sine of theta equals negative r over g times alpha. Now, the radius is also the length of the string. So we can replace the r in this equation with an L. Okay. So finally, we're almost there. We need to get alpha in terms of theta. Well, I've got alpha, but it's in terms of sine of theta. Okay, and by the way, let me go ahead and get alpha by itself while we're at it. So this would become negative g over L, but we got this sine of theta hanging out there, and what I need is a theta. Okay, so what do we do for this? Well, it turns out we're going to do some math trickery. Okay, it turns out for small angles, and we'll define small angles as less than 10 degrees. The angle in radians is roughly equal to the sine of the angle. So for instance, let's try 10 degrees. And I encourage you to grab your calculator right now and try this out, okay? If we do 10 degrees, if I convert that to radians, so I take it times pi over 180, okay, I get 0.17453. Now let's try sine of 10 degrees. So in your calculator, try sine of 10 degrees, and you should get 0.17365 if I round there, okay? You will notice that those two numbers, while not completely identical, are awfully darn close. So we call this the small angle approximation. And we say that for small angles, 10 degrees or less, sine of the angle is roughly equal to the angle in radians. So I am going to substitute sine of theta. I'm going to put in theta instead. So alpha equals negative g over L times theta. Now this is rough approximate, okay? But it works really, really well. And you can try it out for a pendulum. All right, now having said all that, whatever's in front of the theta is omega squared. So omega would be root g over L. Period would be 2 pi over omega, which is 2 pi, the reciprocal of root g over L, which is root L over g. So that is where that equation came from, okay? Now, if we're in class, we will actually demonstrate this and try some times in here, but it works really, really well, okay? Now, for example, if you have a length of 1 meter, that will give a period of 2.01 seconds approximately, okay? So you can solve this for L. So like if you solve this equation for L, you would get L equals, and let's see if I can do that in my head, T squared times G over 4 pi squared, okay? So same thing, like if you have a grandfather clock and you want to make it a specific period, like let's say you want the period to be 2 seconds. So tick is 1 second and tock is a second. Well, you can plug your 2 in here and you can get an exact length of that pendulum for that grandfather clock, okay? Now, this is for a simple pendulum, okay? In the next video, we're going to talk about things that are not just simple balls on a string. Like what if you have a rod swinging back and forth? What is its period of oscillation? And we'll do the same process. We're going to do net torque equals I alpha, get alpha in terms of theta. We'll use our small angle approximation, and that will give us the period as a function of the length of the rod. So I hope that video was helpful, and thank you very much.